When you learn to drive, the most difficult control to master is that of steering. Do you know there are some amazing physics and mechanisms beneath the steering wheel, which keeps the vehicle on the right track without any skidding of the wheels? This video will demonstrate why we need such mechanisms for steering and how they work. We will also understand the workings of power steering mechanisms. We thank Brilliant.org for supporting this video. The amazing thing about an automobile is that if you just tilt the front wheels as shown, the whole vehicle will make a turn. However, why doesn't the vehicle carry on moving in a straight line even after the wheels have tilted? To get the answer to this question, we have to understand the physics behind the most significant invention of mankind, the physics of wheels. In a wheel, which is rolling perfectly, the velocity of the wheel at the contact point should always be 0. This will make sure that there won't be any slippage between the stationary road and the wheel at the contact point. But how can a moving wheel have 0 velocity at a point on its surface? This condition is possible because the wheel has two kinds of motion. The wheel moves along in the direction of the car, and it also rotates along its axis. When we sum these two components at the bottom of the wheel, you can see they are in opposite directions, and they cancel each other out. Just keep this simple principle of a rolling wheel in mind, and you will be able to perfectly understand the steering mechanism. Assume that even after the wheel turns, that the car carries on moving straight. Let's again check the rotational and translational velocities at the contact point of the wheel. You can see that the rotational velocity is inclined, but the translational velocity is straight. Due to this, the velocities will not cancel each other out, and this will lead to skidding. The only way to achieve the 0 velocity condition is to make sure the translational velocity is also inclined. This is possible only when the whole car turns with respect to a particular center point. In this snapshot, this fact is shown perfectly. Here, all 4 wheels meet the perfect conditions of rolling. One major thing to be noted here is that, for such a perfect turn, the perpendicular lines from the front wheels should meet the rear wheel axis at a common point. This condition is the principle of steering. If you observe carefully, you will note that the angles turned by the left and right wheels are not the same. This means that for perfect steering, the left and right wheels should turn at different angles. The steering mechanism is used to carry out this purpose. The most commonly used steering mechanism in modern vehicles is the rack and pinion type. Let's see how this mechanism manages to steer the vehicle. A rack is at the center of this mechanism. This rack is constrained so that it can only move in a straight line. The pinion, which comes from the steering, can make this rack move. A part called a steering arm is attached to both of the wheels. This part is constrained so it only has a rotational motion along the axis shown. The steering arm is connected to the car frame via a roller bearing. This makes sure that it can only turn. A tie rod connects the steering arm to the rack. The tie rod can have both translational and rotational motion. Now, just observe what happens to the wheels when the rack moves. You can see that the left and right wheels are turning at different angles. If you track the meeting point of the left and right wheels, you can see the meeting point always lies on the rear wheel line. Thus, the rack and pinion mechanism perfectly satisfies the conditions needed for steering. Due to this, the vehicle makes a turn without slipping. The steering we have discussed so far was the manual type. Nowadays, electric motor-assisted power steering is widely used on most cars. Electric power steering makes the steering action effortless and more accurate. A column-assisted power steering unit is shown here. Here, a brushless DC motor drives the steering column and the pinion. The motor is capable of rotating in both clockwise and anti-clockwise directions. An electronic control unit decides the amount of power the motor should transfer to the column. The ECU takes the following inputs, such as the torque the driver has applied to the steering wheel, the steering angle, the steering wheel's speed, and the vehicle's speed, and then decides the appropriate torque to be supplied. A Hall effect-based sensor and torsion bar arrangement is used to measure the driver's torque input. Due to the motor's power assistance, the steering wheel rotation becomes effortless for the driver. Do you think this is a perfect mechanism? Wait for a moment and think about what happens to this steering in the case of a motor failing. You might be aware of the fact that a worm screw can turn a worm gear, but a worm gear cannot turn a worm screw. This means that if the motor fails, any manual rotation by the driver will be blocked by this constraint of the worm drive. In short, the steering becomes jammed. To overcome this issue, the rotation from the steering wheel is never directly connected to the worm gear. Instead, it passes through a planetary gear set. Here, the driver's rotation is given to the sun gear. The output is drawn from the carrier, and the worm gear also becomes ring gear of the planetary gear set. During normal operation, power from the ring gear will be easily transferred to the carrier. In case of motor failure, the ring gear cannot move. However, you can see the driver's manual rotation of the sun gear will be transferred to the carrier and finally to the pinion gear.
Power steering units require excellent lubricants to function properly. Fluid breakdown damages internal components and wears grooves into the spool valve housing. Symptoms include whining noises and erratic steering.